Todo lo que se me dice. Yo creo que deberíamos tomar la sala, porque es mala idea. Wow. Pasión y legal.
La puerta ahí, haciendo cola. Se me perdió aquí está, ahí está. Okay.
So, welcome to the second seminar of this year. Today we have Felipe Serrano from Zuse, Berlin. We'll talk about intersection cuts for nonlinear games. Thank you, Felipe.
Thank you. So, yeah, thanks, Marco, for the invitation. Yeah, so I'm Felipe. I studied at the University of Chile, and then I moved to Germany into the SIP, Zuse Institute Berlin. And I worked there for the SKIP team. So there's the SKIP optimization suite. And this morning I realized that I didn't add any slides to talk about SKIP. So SKIP is basically a software, like it's a solver for nonlinear mixed integer programs. So, well, usually it's actually, SKIP stands for solving constrained integer programs. So it's actually like a constrained programming framework, but it's mainly developed for solving mixed integer linear programs and mixed integer nonlinear programs. Yeah, so I'll talk, I think, one slide of how SKIP solves mixed integer nonlinear programs. And yeah, so this is the outline of the talk. It's a bit ambitious. But Diego, you tell me when I have like 10 minutes, and then I'll just give a high-level explanation of what I missed, if that happens. So I'll start introducing LP-based spatial branch and bound, which is the algorithm that SKIP uses to solve mixed integer nonlinear programs and other state-of-the-art solvers like Baron. Then I'll talk about convex underestimator, which is the technique that we use to build the linear programming relaxation. I'll show some drawbacks of this. And then from the drawbacks, intersection cuts should be naturally motivated. So then I'm going to explain what intersection cuts are. From there, it makes sense to think about concave underestimators instead of convex underestimators. And I'll talk about how to build them. And then I'll just talk about a couple of strengthening techniques. And one of them is going to be monoidal strengthening. I'll explain what that is, and if I have time, how it works. Okay? So yeah, just ask me whenever you have a question. Okay. So a mixed integer nonlinear program is a problem of this form, where each constraint is convex or not convex. The fact that the objective function is linear can always be assumed, because one can do a transformation of the form. So minimizing E of x is the same as minimizing t E of x is equal to t. And yes, some variables are constrained to be integers. And well, so here the problem, of course, is the integer this constraint is non-convex, but also there are other non-convex constraints. So this is not the hardest part of the problem. The continuous relaxation is still NP hard of this program. So the way to solve these problems is basically the same as we solve mixed integer linear programs. So basically, we build a linear relaxation of it, then we solve it, Then we try to separate we get the LP solution. If this is feasible, we're happy. If not, we try to separate it and strengthening the relaxation. And the only difference is that when we cannot separate, instead of branching on an integer variable, we branch on a continuous variable. Okay, and I'll show later why this makes sense. So, sorry. Okay. Yes. So the question is basically how to build the polyhedral relaxation, because in the linear case, one just drops the integrality constraint and has the linear relaxation. So here, if one drops the integrality constraints, one still has a nonlinear problem. So the idea is, well, we can start with the bounds and solve the relaxation, and then we need to solve the separation problem. Okay, so we find this going to violate a constraint, and we want to separate this point from this constraint. So separating here, this is usually very expensive in general. If the function is whatever, this is expensive. But there's one case where it's simple. That is when the function is convex. So in this case, one just needs to compute this linearization of the convex function, and this will separate, right? If one plugs in the x star, one gets if this inequality is violated. So the idea is to, when we have a constraint that is not convex, the idea is to find a convex function that underestimates it. Okay? This way, if one finds an underestimator, then the level set of the underestimator is a relaxation. And if it happens that the point is still violated for the underestimator, then we can actually also separate. So for example, consider this nonlinear, non-convex constraint. This is the feasible region. So for example, here we know that the exponential is not negative. So we can lower bound this expression by just the x squared plus y squared. This defines this convex relaxation. And then, for instance, if we had a point here, we could build a cut that separates it from the region. If the point is inside here, then we cannot separate. Okay? So this is, of course, a very ad hoc argument. I mean, I know how the function looks like. So what we do usually is, if the function is simple enough, we do know how to build underestimators. You know. And when the function is not so simple, then what we do is we just make it simpler. So this is what Skip would do. Skip would take this constraint, and it would introduce new variables, and it would replace the complicated expression by these three constraints. Now, this is a simple enough constraint, so we know how to build underestimators for this. We also know how to build underestimators for this, and this is convex, so this is okay. So, and the trick for doing the product here is to use the Mccormick inequalities that I'll talk again later, but these are the Mccormick inequalities. So this is what would happen. So as I said before, sometimes it happens that the point is not separable. So say we have such a constraint, so is the graph, and then in some domain, so say between here and here. So the convex hull of the constraint is the red region here. So it's defined below by the function itself, by the x squared, and above by the secant. Okay. And if it happens that the point is inside the convex hull, of course, we cannot separate. And here we would do the branching. So when we branch on this value, on x, on this value, then we would get one subproblem that is this side here. And now the convex hull changes, and actually the point is separable. And on the other problem, the same happens. Okay? Of course, this is a 2D example. In more Ds, one sometimes need to branch more in order to be able to separate. Okay? So, how, well, I'm going to talk about how we build convex underestimators in general. So actually, we do this splitting of the function, if you want, but you don't really need to do that. So the idea goes back to McCormick, to the 76. And yeah, so first, when we have so let's take this function, we have the domain 0, 1. So the convex envelope is the largest convex underestimator of the function. And this is what we would like to have. This is like the best, the best we can hope for. Usually, well, the way that we would build the underestimator, because computing the convex envelope is very hard. It's MP hard. It's very expensive. So, but a simple way would be like here, we realize that the only non-convex term is the minus 12x cubed. And if one underestimates the minus 12x cubed by this, and then underestimates the whole function by keeping everything except the minus 12x cubed, one would get this convex underestimator. Not so nice. And the convex envelope is actually given by this. You see the straight line, like the secant until this point, and then it's the function itself. This will be the convex envelope. So yeah, sure, the convex envelope is the best, but we cannot really get it. So what McCormick did, he built a procedure. He proposed a procedure for building convex underestimators for a very large class of functions, the class of factorable functions. So basically, factorable functions are functions that one can build from a given library of functions. So we start with some simple functions, and then we form the set of all the functions that we can build from these functions that is closed under addition, multiplication, and composition. With this, we can build very complicated expressions, like, for instance, here is the recipe for building such a function from the library and these operations. So yeah, so this is the definition of factorable functions. Equivalently, one can think of factorable functions as functions that have an expression tree when one evaluates them, for evaluating them. So the definition is somewhat inductive. So basically, we have the basic functions, and then we build any other function either by addition, multiplication, or composition. So McCormick proved that each factorable function admits a convex underestimator by basically by induction. He suggested some underestimators for the library functions. Then he proposed how to build an underestimator for the sum of two functions for which we know the underestimator, or the product, or the composition. So the simple functions one just needs to compute stuff, and one gets the underestimator. Then the sum is clearly just the sum of the underestimators. So these two are easy. And then we have to find out how to build the underestimator for the product and for the composition. So the idea for the product is what is known as Mccormick inequalities. So basically, they come from the following. So if one has that, so one has a function over some domain, and one notes a lower bound of the function, say. And so one has the other function, also knows a lower bound. Then one knows that this product is non-negative. And when one expands this, one gets, for example, the first inequality. And changing whether one uses the lower bound or the upper bound, one gets the other inequality. And well, this is for the lower side, and then there are also two inequalities for the upper side. Now, this expression here is an underestimator for this one, but it's not necessarily convex, right? Because the F doesn't need to be convex, the G also doesn't need to be convex. But the hypothesis is that we know a convex underestimator for F and for G. And we also know a concave overestimator. So for example, if this number here is negative, we need to use a concave overestimator so that this term here is convex and underestimates. And we use the convex underestimator if the number is positive. Okay? And for the composition, Mccormick came up with the following function. One has a convex underestimator of f, one has convex and concave under and overestimators of g, and then one solves this optimization problem, this function. So basically, the function defines the range of the set variable and then the minimum here. So there is an explicit formula for this, the solution of this. But yeah. So usually people don't do this because they hide the composition in the splitting of the function. When I said that one makes the function simpler and one introduces extra variables, this means that the composition is hidden in the new variables. So one doesn't really need to do this. But if one doesn't want to introduce extra variables to the problem, then one would need to build the underestimator like this. Okay? So for example, seeing that this function underestimates is not so complicated, one realizes that g of x is a feasible solution here, right? Because the convex underestimator and the concave overestimator, well, the function is between. And then we get here that the convex underestimator of f evaluated at g of x is a feasible solution. So, and this is already smaller than f of x, f of g of x. So, yeah. And to prove that it's convex is just by definition. One just needs to work out the definition. Okay. So what are some drawbacks of this? So the algorithm looks very much like the algorithm that we use for solving mixed integer linear problems, right? But what happened actually if we try to solve a mixed integer linear program using this algorithm? So consider a binary problem. And we would need to model first the binary constraint as this nonlinear constraint. Okay? This is the same. This is it's just looks like, so this is 0. It looks like this. Something like that. Okay. So it needs to be less than 0. So the feasible region would be this one and this one. And of course, one has the bounds of 0, 1. So the only feasible points are these two. So then we solve the p-relaxation, and we're going to get a variable that is, we're most likely going to get a variable that is not binary. And then we need to solve the separation problem. We need to separate the LP solution, the value of that variable, from this constraint. But this can never be done because the point belongs to the convex hull of the feasible region, right? So then we would need to branch. So this is a terrible algorithm for solving mixed integer linear programs. So it's not quite a generalization. So then the question is, how do people that solve mixed integer linear programs get around this issue? Well, the trick is to realize that if the variable actually achieved a variable that is not 0 or 1, it means that the variable is basic, right? If we solve the P with the simplex algorithm, this variable has to be basic because it's not the bounds. So there has to be in the tableau. The tableau tells us that we can express this variable as a combination of other variables, right? Like this. So then, like this, sorry. So like, then the constraint that xi has to be in 0, 1 is equivalent actually to the constraint that this expression has to be between 0, 1. And from there, people build Gomery cuts or whatever. Okay? So, yeah. Remember also that the non-basic variables are non-negative. So while here we were separating, here we are separating the point when the variable is xi, is the xi star. Here we are separating the point 0, when the non-basic variables are 0. This is the point that we're separating here. So let's do the same for the MNLP setting. So we saw the pre-relaxation on the tableau will tell us that all the variables are equal to some point plus the rest of the tableau. Okay, here I'm including, usually one writes only the basic variables equal to a function of the non-basic variables. Here I'm including all of them. So here the basic and the non-basic variables. Okay. So then when we have this constraint, it's equivalent actually to this new constraint, only on the non-basic variables. Okay. And the nice thing is that actually the point that we are separating now is 0, which is a vertex of the domain of this new function. Okay. And one cool thing about the convex envelope is that actually the convex envelope coincides with the function at the vertices of the domain. Okay? So this means that if we could build the convex envelope, it would be equal to the function, so the convex envelope would be violated, and then we can separate. The problem, of course, is that we cannot build the convex envelope. And but maybe the construction from Mccormick also has this property that is tied at the vertices. But sadly, it doesn't. So the thing is that when one has FOG and then Mccormick builds the convex underestimator for the composition, so it takes a convex underestimator of F and solve this problem here. So this is a convex and this is a concave. The convex underestimator of F, this has to be in the range of G, over the range of G. So the change of variable that we're doing here is just a linear change of variable. The range of this expression is usually going to be the same as the range of the variables that we had originally. So there's nothing really to be gained from doing this. But still, the idea that we can always separate it's interesting. So let's look at an example. So let's look at an example where when I was thinking of this, I said I didn't really believe that you could always separate. So I said, okay, I'm going to build an example where the feasible region is the outside of a ball, and the p-solution is this point here. So this, for me, is the worst case of non-separability. Okay. So this is what I came up with, the following problem. So this is the outside of the ball, and these linear constraints are going to force me that the p-solution is going to be there. So how does this look like? So this is the feasible the linear relaxation. If I remove the ball constraint, is this tetrahedron. And the nonlinear constraint tells me that, well, it's the outside. Well, this is it. And we are minimizing Z. So the optimal solution of the linear relaxation is going to be this point here. And when we look at the constraint, we're going to see this. Right? So one solves the P, computes the optimal tableau, and then changes so we realize, of course, that the point here, the basic variables are X and Y, right? They are not in the boundary. So even though it's 0, the bounds are -1 and 1. So these are basic variables. And here we see the tableau, and then we replace the X by whatever the tableau says. So the new constraint looks like this now. So let us look like what happens in what is the feasible region of this constraint. So here it is. So the interesting thing is that, so the original feasible region was the cube. In 3D was the cube and the cylinder in the middle. If we only look at this constraint, at the nonlinear constraint. So now the cylinder got tilted, And the point that we're separating is this one, right? The origin, 0, 0. So, well, clearly it is separable, right? One can imagine a cut there. But actually, a way of building a cut here is if one can take this point here, and that point there, and pass a hyperplane through there, right? And that is exactly what intersection cuts do. Okay? So let me talk about intersection cuts now, and then I'm going to come back to this. So this is a bit of a more abstract explanation, more functional explanation of intersection cuts. So I'm going to try to give a graphical one here. So we assume we have some feasible region, something. I don't know. And we also assume that we have a cone that contains the feasible region, polyhedral cone. So it's generated by some rays. And we also, so this is 0, the feasible region doesn't contain the 0. And we assume that we have a convex set that doesn't contain any point of the feasible region in its interior. So actually, this can happen. It can touch. We have this convex set C, and it contains the 0 in the interior. Okay? So the thing is that we can represent convex sets as level sets of convex functions. And we say that, that a function represents a convex set if the function is sublinear and the convex set is the one level set of it. So this sublinearity it just means that the function is convex and positively homogeneous. And positively homogeneous means that this, basically that. If lambda is non-negative, then we can take the lambda out of the argument. So these functions are the functions whose epigraphs are cones, basically. So for example, the absolute value of x is convex and positively homogeneous, is sublinear, the norm, the 2 norm, and there are more. So there's of course, a canonical representation of any convex set, which is its gauge functional, in case you know it. So it's given by the infimum of lambda greater than 0, such that x is in lambda times 0. So it's basically how much we have to expand or contract the set so that the point that we have is in the boundary of the set. Okay? Oops. Sorry, I did something. Yeah. So the gauge of the set will always satisfy that. Okay. And so now, since the set C, we chose it so that it doesn't contain any feasible point in the interior, we know that for a point to be feasible, it cannot be in C, right? And we know that since the rho is a representation of the set C, we know that x is not in C if and only if the rho of the x is greater than 1. Okay? But it's not in the interior of C if it's greater or equal than 1. Okay? This is what we know. And we also said that there was this cone that contained the feasible region, so we can write any feasible point as a conic combination. So this is actually a cut. This is already a separating inequality, right? If one plugs in 0, one gets 0 here, so it's violated. But this is nonlinear. So one is equivalent to replacing the x by the conic combination, and then one applies the sublinearity of the function to get this linear inequality. Okay? So these are intersection cuts, and the raw function there is known as a cut generating function. The reason is, okay. So the idea usually is that one has a linear relaxation of a problem, and these rays here are given by these are the non-basic variables, basically. So one solves here, and one gets the basic variables are equal to some value plus some rays on the non-basic variables. And one can find, for example, say, one entry here, xi has to be binary, but one gets that, say, xi is equal to a half plus whatever, some other variables. And then one would get, one can rewrite this as that this sum has to be in 0, 1 minus a half. Or one can even relax this and say it has to be integer and minus a half. So this would be the set S. It doesn't contain 0. And a convex, so the feasible region would be, so this is 1 minus 1, 0. So the feasible region would be half minus a half, this and that. And then one can take C as this set here, minus a half, half. And one has this, the rays in this picture, they look like, yes, this would be R1, R2, whatever. And then one builds the gauge of this set, which is nothing more than, it looks like this. So this is a half and minus a half. The function is, this is 1, would be like this. And then one just evaluates this function at this rays, and one gets the cut. So these are the coefficients of the, so when one builds a Gomery mixed integer cut, the continuous variables get this coefficient, basically the one given by this example, from this S-free set and everything.
But is it easy to find C in general?
So in the mixed integer case, in the linear case, yes, it's usually this always. So one always gets something like this when one looks at a single row, right? And then it always looks like this, let's see. And for the nonlinear case, I'm going to talk about now how to build such a C. Okay? So why could we, in this picture, why could we actually build this cut? What happened here is that the constraint was concave. And this is the good thing. Because now here, the rays are just the canonical vector, the basis. And the set C, in this case, is the complement of the feasible region, right? It's just the cylinder. This is a convex set. It doesn't contain any feasible point. And then one can just build this cut, which is equivalent to the one that one would get using the gauge function. So yeah. When the constraint is concave, then the complement of the constraint would be the C that we're looking for. This is a convex set, doesn't contain any feasible point, right? The problem is that we don't usually have a concave constraint. So, but the idea is then that, well, whenever we have an underestimator, we get a relaxation. And if the underestimator in this case is concave now, then the complement of the relaxation is going to be an S-free set, So this is the idea. Build a concave underestimator of the constraint, and then consider C this set. Okay? And then, well, the obvious question is, okay, how do we build this concave underestimator? Okay, is it clear, this point? Okay. So, well, the definition of a concave underestimator is we're going to define a concave underestimator at a given point. So the nice thing about concave underestimators is that one can imagine that concave underestimators always exist. One has some function, whatever, and one only needs to be able to, when we want to be tight there, we just need to go to minus infinity fast enough, right? This would be a concave underestimator. Yeah. So building, like, there should be many of them. We don't have the problem with convex underestimator that a convex underestimator might not exist, right? Or even the convex underestimator depends on the bounds. I'm going to talk about that later. This one doesn't really care what the bounds are. Okay? So we're going to define a concave underestimator as an underestimator that is concave and is tight at a given point. And the same way we define a convex overestimator. Okay, so okay, let's think about how to build these guys. So one way is, well, if we take a function and we write as a difference of convex, and then we linearize the convex part, we're going to get an underestimator that is concave. The nice thing is that difference of convex, like almost every function can be written as difference of convex. Like there's a theorem that tells you that if the function is C2 over a compact space, then it is a difference of convex. Every factorable, one can prove, Tui does it in this book, every factorable function is DC. The problem is that the results are more existential. There exists a difference of convex decomposition, but writing it down is not so simple in general. So, okay, this is, so yeah, so one example. So X times Y, one has this identity. This is convex. This one is also convex. One would linearize this one and get a convex underestimator, a concave underestimator. Okay? So, okay, so let's discard this idea. And then, so then let's try to build it like Mccormick did for the convex underestimator. We now try to follow the same recipe for the concave underestimator. So we first need to look at the library functions. So the exponential is convex. A concave underestimator of a convex function is just the linearization of the function at the point, right? So we have a convex, and then we want to build the concave underestimator at this point. It needs to be tight here, so we just linearize. This is a concave function, the linear one, and it's an underestimator. Good. The logarithm is concave, so it's its own underestimator. The cosine, whatever, has bounded second derivative, so one can easily write a DC decomposition of it, like this. This function is, one can prove easily that is the second derivative is always non-negative, and so on and so forth. Okay? Good. How do we do the sums? Well, the sums is, like the convex case is easy, it's just the sum of underestimators. The composition. So McCormick said that this one was a convex underestimator for the composition. And funnily, if one just tries to do the same, but changing the convex by concave and what needs to be changed, then it works. So this is a concave underestimator for the composition. And for the product, one uses the identity that I showed before. And now, well, this is a sum, so we know the underestimator for a sum. We know for the difference was the same. So it reduces to compute the underestimator for the square, right? But the square is a composition. So we can use this result here to do that. So how one underestimates plus and minus the square. So, well, I don't want to go through the details, but here, this is a concave underestimator. By the way, I didn't say. So this has an explicit solution. So this is a objective function is concave over an interval. So the solution is going to be one of the extremes, the minimum of them. So this is an explicit formula for this, for the concave underestimator. Okay? So here we have the concave underestimator for minus h squared. And for the h squared, one would need to linearize first the x squared, the convex part, and then, well, do some case analysis. But this is it. So let me show you some examples. So we want to build an underestimator for this function here. So we first, well, if this idea of factorable function, it's built like by steps. So we have to follow the steps and build the underestimator in this, along we're building the function. So first, we will need to build underestimator for what's inside the square, and then the one for the other. So one can compute, and it takes a bit of work, but one can do it. So one gets this underestimator for the cosine square, for cosine of x squared plus x fourth, and this overestimator. So this is the function, the convex overestimator and the concave underestimator. Okay, and then with this one can build the one for the square. The one is use the composition result, and one would get this function here. So here you see that the minimum starts showing up. So it's one function, and then the other function is smaller than the other. So. Okay, nice. So how long? 15. Okay. Good. So, okay, as I said, the nice thing is that, well, we don't need bounds, right? But actually, it's not really that nice, because we're not going to do a cutting plane algorithm. We're not just going to cut. We're going to start branching at some point, right? And then, oh, by the way, if you were wondering, such an algorithm, like we can always cut the T solution. So one could wonder whether such an algorithm converges. It doesn't. It doesn't converge in general. So this was shown a long time ago. So, okay. So yeah, so as I said, a big difference is that this one doesn't depend on bounds. But when we branch, we're going to basically strengthen the bounds. And we cannot really take advantage of this so far. So the idea would be to find out a way of, well, taking the bounds into account. And the idea why the bounds could actually help is the following. So suppose, 1D examples are not so good, but okay. So suppose we have a function like this, and the feasible region would be this here. Okay? And say the bounds are between here and here. Okay? And we get this solution here, and we're computing the intersection cut. So we have some ray pointing in that direction. So, well, I didn't really say it, but the intersection cut, what we need to compute is, oh, I did say that. So what we need to compute is when does this ray touches the boundary. Yeah. This 1 over this number would be the coefficient of the cut. But it doesn't matter. So the thing is that, okay, so this is what we have. But actually, by the way, this function say the actual constraint, whatever was, I don't know, like something like this, and then, I don't know. So this is a concave underestimator already. Okay? So what we need is, we only need to underestimate the function on the domain. I don't really care what happens here afterwards. So for example, if I could continue linearly from that point on, okay, the red one now is not an underestimator, but it is actually an underestimator on the domain that I care about. So now the S3 set wouldn't be this one here. It would be the whole thing unbounded. And so the cut would be stronger. So this I also didn't say, but the larger the S3 set, the stronger the cut. Okay? So this is the intuitive reason why the bounds could help. So TUI. Oh, I didn't talk about the history of these things. So intersection cuts were introduced by Balázs in the 70s or something. But actually, TUI already introduced a type of intersection cut, though he didn't call it intersection cut, in 67 or something like that. And then he proposed something that I don't think he proposes as a strengthening. Maybe, yeah. I don't remember. The paper was in Russian and I had to use Google Translate, so I'm not so sure. But yeah. So the idea is, okay, so we know that if a function is concave and differentiable, we can write it like this, right? It's the minimum of linear functions, namely its linearization at each point, right? So if we do have bound, we only need to compute the linearizations inside the domain. So this is what happens in, well, this is exactly what would happen here. So what I'm saying is that you have all these linearizations of the function. The minimum of them is the function itself. But if we compute the linearizations only in the domain, then it will stop here. We will get this last linearization. And now the function is going to be described. So the TUI strengthening would be described by the red one here. Okay? So this is already a strengthening. And the strengthening that the new strengthening that I propose is, well, it's basically the same, but actually, I don't really, the thing of the relaxations of the underestimator is that, so this is kind of the idea. So when one has, the constraint is this, G of x less or equal to 0. So this is the set that I need. When I have an underestimator, what I know is that whenever an x is such that g of x is less than 0, then the h of x is going to be less than 0, right? This is what the underestimator enforces, right? But I don't really care that the h is actually smaller than g. I only care that it's non-positive when the g is non-positive. This is what I really care about. So then, the strengthening would add this extra condition there. So one can prove that this function is still concave, and g hat greater or equal than 0 is an S3 set. So let me just show you an example. So here we have this quadratic constraint, which is represented by the blue region here, okay? Doing an eigenvalue decomposition, we can write it as a difference of convex and linearize the convex part, and then we get a concave underestimator of it. The level set of the concave underestimator is the, I don't know what color that is, orange or yellow region there, okay? And we are looking only at this is the domain, this black box and here, okay? So say we could get, as an LP solution, a point inside here, and then we would have some rays, and then we would need to compute where it intersects there or there, and then we would build the intersection cut, okay? So the TUI strengthening gives you the following. So it's a little bit bigger, the set. They coincide inside here, but outside is a bit bigger, right? They have to coincide inside because inside it's the same function. Yeah, so it's a bit bigger. But the interesting thing is that actually what one would like to, is to continue linearly here, right? I mean, why do you need the curvature, right? And the tree, where you can see it a little bit, still has the curvature. And now by adding this extra constraint, this one there, one would get this one here that goes linearly outside. Okay? Of course, computing this is right, like the feasible region is convex. So because G is concave, so the upper super level set of it is convex, but the objective function could be non-convex. Though in the case of quadratics, it is actually convex, but still, you have to remember that when we compute the intersection cut, we want to find the point where it intersects. So we need to find a zero along a line of this function, which is, well, it's complicated. It would be a bit expensive, even if everything is convex. Okay. Good. So how long do I have? 5 minutes? Okay. So I don't think I have time to explain monoidal strengthening. Monoidal strengthening is a bit more involved. So yeah, I'm gonna give a high-level idea of what's going on. So the idea is that, well, yeah. So the slides here are a bit also more dense. So remember that we had for the intersection cut, we had something like this, right? For the integer case, we had like a half and a sum of some raised. So this has to be integer. So here we are never really exploited. We only exploited the fact that the non-basic variables were non-negative, right? This was the solutions, the vertex, and also in this when we build the cut, when we use the fact that the function was positively homogeneous, we can take the xj out of the argument because it's non-negative. But we don't really exploit the fact that maybe some non-basic variables are actually integer. Okay. So the idea of monoidal strengthening is to, so suppose, I think I have an example. Yes. So suppose we solved the pre-relaxation and whatnot, and we got such a, so after replacing the basic variable by the tableau row, we get such a constraint that this expression has to be in set minus a half. And suppose now actually the non-basic variables are integer. Then we know that this number here is integer. So this new expression here, we can write it as the old expression plus this thing here. And this term is also going to belong to S because this is integer and basically set minus a half plus set is the same set minus half, right? But now what we did is we changed the coefficients here. Yeah, and actually we can do the same argument with any number, any integer number there, right? And so the cut, we have this infinite number of cuts here, and one of them is going to be the best. So then one can choose the best. So this idea of monoidal strengthening. So why it's called monoidal strengthening is because, well, so this is the theorem that Ballas and Jaroslaw proved, is that if one have so suppose whenever you have such a relationship, then you can deduce a cut. Like in the intersection cut setting, you have that this has to be in the integers, and so you have such a cut from an S3 set. So then, if M is a monoid, like set. Set is a monoid. Monoid is just closed under the operation and has a neutral element, and the operation is associative. Then one can change the cut coefficient in the same spirit as this example. So this is the idea. And the proof is, well, basically what I said. One can add some term, and this is going to be in the set plus the monoid. And since it is a monoid, the monoid plus the monoid is the monoid. And then one can get a new cut, and then one can choose the best coefficient for the cut. Okay? So the idea of how I understand monoidal strengthening is basically we have some relation, and we want to, with some extra information, build a new relation of the same form. This is the idea. And the point is that one can apply monoidal strengthening to disjunctive cuts. So I'm not going to talk too much, but too many details. But one has a valid disjunction, one can get a disjunctive cut that looks like this. And then the idea is, okay, we have a disjunction. How can we build a new disjunction? And what Ballas did is, Ballas and Gerolov, they said, like, okay, if we had a lower bound for each of the disjunctive terms that make it each disjunctive term valid, and by this I mean, and I'm going to finish now. So suppose you have a disjunction like this. So you are either here or you're here. Okay, so this is a non-convex region, the disjunction. Okay. So what one means by this lower bound is this is a disjunctive term, this inequality state. So this is alpha 1x greater than 1. And the lower bound is, so the feasible region here, we are assuming also that the variables are non-negative. So the feasible region is this thing here and here. So one can relax this down up to this point, right? And now alpha 1x greater or equal than beta 1. And now actually this is a valid inequality for the whole problem. So this is what is meant by this lower bound. So the disjunctive term, this is not a valid inequality, right? Because it's violating the points here, this one. But the lower bound makes it valid. So with this lower bound, one can build a new disjunction using some trick. I don't have time to explain. And yeah, so then one get a strengthened cut. So the point, like how we can apply this to our setting, is that each of these convex S3 sets define naturally a disjunction, right? You have to be outside the convex set. This is an infinite disjunction. One can linearize all the boundary of the set, and then one can apply the same technique, but it's super expensive and not easy. There are some problems that I cannot talk about, but here's an example. So the feasible one variable is integer, the other one is continuous. So the feasible region is this line, this line, this line. The intersection cut here would be this cut here. And when one applies monoidal strengthening, well, one can strengthen the cut up to there, which is actually valid. Okay. So yeah, the summary is that one can always separate the P solution with intersection cuts, and one can build convex S3 sets by building concave underestimator of functions. And since the method applies for factorable functions, then this is applicable to a large class of problems. And we are working in the implementation of this technique in Skip. And yeah, well, some open questions: how can we make the strengthenings performant? And when can ensure that the convex S3 sets are maxima? When, how can we, in which cases can we say that the convex S3 set can, there's no other convex S3 set that contains this one, so that the cut is the strongest that it can be. That's it.
Thank you.
Thank you.
So I assume you're looking at into the programming literature for all these things too, right? This is
Yes.
monoidal strengthening. What Badash essentially shows, right, is that a lot of these things is equivalent to pivoting to different bases, right? And applying the disjunction there, right? So you could use that kind of heuristics like the Sketi or things that Sanjeev and I did, just to move through bases and do something quicker and cheaper maybe than.
Yeah, sure. The idea of pivoting to another basis is that you change the cone.
Yes. Exactly.
The cone relaxation that you have, which can give you deeper.
And if you look at the text, you can actually know which way to get strengthening or stuff, but you can just randomly do it.
Yes, yes.
So do you have any idea how it works? Any experiments with simple functions? Or?
So we are implementing it for quadratic constraints. And so far, we haven't seen very good results. But we recently came up with a way of generating better concave underestimators so that the S-free sets are actually bigger now. And we're going to try this now.
The computational goes with computing the underestimators.
No, yeah, well, it's complicated. There's a tuning issue going on because of the way Skip is implemented, and we're implementing this. It happens sometimes that Skip can cut too much, so it can cut and cut and cut and cut, and it doesn't start branching. So it gets stuck on cutting. So we need to have better limits, and of course, numerical issues also rise. The cuts can be very dense because it's the tableau. The road.
First, you're just trying to prove the bound. If its speed is probably secondary, right?
Yeah. So yeah, we haven't. I think. No, we're working on the root gap experiments also. But I don't have numbers. There are some instances where it, of course, works better, and some others where it doesn't.
So if the S set contains 0, then what do you do? Have you shift?
No, the point is that the S set never contains 0. So basically, you solve the P relaxation, and you get a point that is infeasible, right? And then you shift everything so that this infeasible point is 0. So that's why the S never contains 0. 0 is a bit simpler to talk about things. So you can do everything translated, but yes.
Thank you, Felipe, again.